Good afternoon, students. We'll start with the today's lecture. In the previous lecture, we have seen the Stokes theorem and we have solved the numericals based on that, right? So line integral is related to the surface integral, right? The next, in the second numerical was wrong and I have sent the solution through WhatsApp. Just please go through that. And also solution is there in the PPT also, right? Okay, we'll start with the today's lecture. The topics that are going to be covered is magnetic flux and magnetic flux density. Then Maxwell's equations for static electromagnetic fields, application of flux density and flux to coaxial cable, and one or two numericals based on that, right? Okay, already we know the relationship between the magnetic field intensity and magnetic flux density B, right? B is equal to mu naught H, that is in the free space. Then we'll try to establish the relationship between magnetic flux and magnetic flux density. Magnetic flux is represented by phi and magnetic flux density by letter B, right? Okay, we have already defined the magnetic flux density as flux passing through unit surface area. So if I want to find out the magnetic flux phi, then surface integral of B dot ds, Webers is the unit of the magnetic flux, right? Okay, then next, we already know this relationship B is equal to mu naught H for free space, right? Okay, the unit of the magnetic flux density is Weber per meter square or Tesla, and mu naught is the permeability constant, right? 4 pi into 10 power minus 7 Henry per meter. Okay, these equations just similar to your Gauss law. This Gauss law we know with respect to static electric fields, we know psi is equal to closed surface integral of D dot ds equal to Q. This is the Gauss law. Then what is the similarity? Means similarly with respect, just like Gauss law, what is the Gauss law for magnetic fields, right? So this is the equation, closed surface integral of B dot ds equal to 0. Means suppose I have any closed surface, right? Okay, and I have the magnetic field lines or flux lines, right? So let me assume that yes, this is just current carrying conductor is generating the magnetic flux lines like this, and this is the closed surface, right? So the number of magnetic flux lines entering the closed surface is equal to the number of magnetic flux lines leaving the closed surface. Means the total amount of magnetic flux density within the closed surface is 0 only, right? Because the number of magnetic flux lines entering the surface is equal to leaving the surface, right? So the closed surface integral of the magnetic flux density over the closed surface is equal to 0. Closed surface integral of B dot ds equal to 0. Okay, next we have seen the divergence theorem with respect to static electric fields, right? So what is that? Just let me write the divergence theorem here. Closed surface integral of D dot ds, right, is equal to volume integral of the divergence of D vector over the considered volume dV, right? So similarly, I can apply the divergence theorem for this. So del dot of B into dV, right? So del dot of B, what is this del dot of B? Similar to del dot of D. If I apply the divergence for the electric flux density, it is fine. But here, if I apply the divergence for the magnetic flux density B, then it will be 0 because LHS equal to RHS, right? Similarly, I can write closed surface integral of B dot ds is equal to volume integral of the divergence of B vector into dV. But in the closed surface it is 0. So hence I can say del dot of B vector is 0, right? I hope you understood this. So we have several equations, for example Ampere circuit law, point form of Gauss law, right, integral form of Gauss law, all those things we will list out those equations with respect to static electromagnetic fields, okay, in the next slide that we are doing. So those equations we are listing here, this we call it as Maxwell's equations for static electromagnetic fields. The equations, just I will write the numbers for it, 1, 2, 3, 4. Similarly, these are the equations in integral form. These are the corresponding equations in point form here, also called as differential form. Differential form, this is integral form. So first we will consider the Gauss law. Yes, Gauss law in integral form, we know that closed surface integral of D dot ds equal to Q, and Q is equal to volume integral of rho v into dV. This is the integral form of Gauss law, we know it. Then what is the point form of Gauss law? We already know this. We have already studied all these equations. Just we are listing out here, that's all. So in point form or differential form, del dot of D vector is equal to rho v. This is the point form of Gauss law. The next, conservation of electric field. With respect to conservation of electric field, we will see certain laws here. conservation of electric field. Yes, principle of conservation of electric field or field, we know that closed line integral of E dot dl equal to 0. This we have seen. Then similarly the point form of it or differential form of this conservative of electric field is del cross E equal to 0. Yes, curl of the electric field intensity is 0. This equation also we have seen. Is it fine? The third one is Ampere's circuital law. Already we have studied this. Ampere's circuital law. Yes, in integral form, closed line integral of h dot dl equal to I. And the relationship between I and j we know, that is I and current density. I is equal to surface integral of j dot ds. This is the Ampere circuital law. Then point form of or differential form of Ampere circuital law is curl of h is equal to j. Right? This is the point form of Ampere circuital law. The next, lastly, that is conservation of similar to your conservation of electric field, we have conservation of magnetic flux. Conservation of magnetic flux. So this equation in the previous slide I have told you, right? So closed surface integral of B dot ds equal to 0 because the total amount of magnetic flux lines entering the closed surface is equal to leaving the closed surface. Hence, the closed surface integral of the magnetic flux density over the closed surface is equal to 0. So this is the integral form, and point form corresponding to it is del dot of B equal to 0. This we have proved using the divergence theorem, right? Okay. And okay, these are the set of Maxwell's equations as applied to static. Please keep in mind static electromagnetic fields. Similarly, we have another set of equations of Maxwell's equations, integral form as well as differential form, also called as point form, for time varying electromagnetic fields. That we'll see later. For time varying electromagnetic fields, this is for static electromagnetic fields. You should be knowing it, right? Okay. Next, we'll see the application of the flux density and the flux to the coaxial cable. Okay, with the help of the flux density concept and flux, we will try to derive the expression for flux between the conductors of a coaxial cable using the concepts of flux density and flux. We'll see it, right? Okay, this is the coaxial cable having this is the inner conductor having radius A, right? It is extended here. Similarly, we have the outer conductor. So this is the inner conductor whose radius is A. Then similar to which we have the outer conductor, right? Just let me mark it. Okay, inner conductor whose radius is A and outer conductor whose radius is B. In between inner conductor and outer conductor, so we have the dielectric material as air. Let us assume that air is filled here, right? Okay. Then now initially, and we will align this coaxial cable along z axis. This is the z axis, right? We are aligning along z axis, and initially we will assume that this is infinite length conductor initially, right? And we'll assume that the current I is flowing through the inner conductor in this direction here along z axis. The current I is flowing in the inner conductor along the positive z axis. Then what is the current that is flowing in the outer conductor? It is exactly equal to the current that is flowing in the inner, but in the opposite direction. You can observe here, it is in the opposite direction here. It is shown here, right? So the current I in the outer conductor, it is flowing in the opposite direction, but magnitude is same, right? Okay, I hope you understood this diagram. With this diagram, we will proceed. Okay, initially we have assumed that it is infinite length conductor. So we know the magnetic field intensity H due to the infinite length inner conductor. Let me take the right. We know the magnetic field intensity due to the current carrying infinite straight current carrying conductor. So in region lying between A and B. Suppose let me take one region here. Let me assume this is the region we are taking. Let me draw it with dotted line. I want to find magnetic field intensity in the region between A and B here, right? So this inner conductor acts as a inner conductor which is having infinite length and carrying a current. So we know the magnetic field intensity H in region lying between A and B is given by H is equal to I by 2 pi rho into A phi. So R and rho, don't get confused, both are one and the same. In some textbook they use R, in some textbooks they use rho. It is cylinder, right? Don't, by looking at R, don't say that it is a spherical coordinate system, right? It is cylindrical coordinate system only, right? Okay, H vector is equal to I by 2 pi rho into A phi ampere meter, right? R is lying between A and B. Then we want to find out the flux between the inner conductor and outer conductor. We want to find out what is the flux here, right? Okay, we'll proceed. We know that already H So we know the flux density, magnetic flux density B. Yes, we have assumed dielectric material is air, so we can make use of this relationship. B is equal to mu naught H for free space or air, right? So mu naught into H, already H due to infinite length conductor is I by 2 pi r into A phi, substituted Weber per meter square. R is lying between A and B. Then next, initially we have assumed that it is infinite length conductor, but we will put the restriction on the length of the conductor. Let us assume that this is having finite length. The length of the coaxial cable is d. So this is situated along z axis. At this surface, let us call this is at z equal to 0. At the other end, z is d, z equal to d, right? These are the two ends of the coaxial cable, and total length is d, right? So let d be the length of the conductors. Then we know the magnetic flux definition. Magnetic flux phi is equal to surface integral of b dot ds, right? Okay, we know what is b already. It is here. This is the b, right? We have calculated. This is b. What about this, right? Okay, this is in phi direction, right? So current I is flowing in this direction, means use the right hand thumb rule. The flux phi, it is in phi direction. So what is the differential surface area? This should be normal to the phi direction. So differential surface area along phi direction I want to find out. So since this is cylindrical coordinate system, so the scale factors are 1 rho 1 and differential elements are d rho, d phi and z, dz. I want to find out differential surface area along phi direction. So leave this phi direction, means leave this, multiply 1 into 1 is 1, d rho into dz. So d rho into dz into a phi. I hope you got it. So next we came to know what is ds. So just take the dot product of b vector and ds vector. So it is written here phi equal to surface integral of b dot ds. B is written. Then next this is b. Then next ds, right? Okay, a phi dot a phi will be 1. Then what about rho and z? Rho is varying from the radius, right? A to B. It is A to B. The next, z is varying from the length of the conductor. Z equal to 0 here, z equal to d. So z equal to 0. This is z. Then z equal to d. Right? Okay, integrated. So after integrating, just integration steps are given. You can have a look at it. So the flux, this gives the flux between the conductors of a coaxial cable. That is phi is equal to mu naught I into d divided by 2 pi into ln of b by a. These are the fractions, or yes. Okay, a and b are the radius of inner and outer conductors. Okay, d is the length of the coaxial cable. I is the current that is flowing through the inner conductor, and it will be exactly opposite in the outer conductor, right? Mu naught, you know, 4 pi into 10 power minus 7 Henry per meter. Okay, this is the simple derivation in order to find out the flux that exists between the inner conductor and outer conductor. Yes, as the length of the coaxial cable increases, what will happen? The magnetic flux will also increase, right? As the length of the coaxial cable increases, the intensity of the flux lines will also increase, right? Next, we'll take up this numerical. Okay, a radial field H vector. Yes, in the morning class, this was the mistake. It is not minus, it is divided by. I thought this was minus 2.39 to 10 power 6 divided by r minus. It is not minus, it is divided by. Okay. So H vector, let me write it. H vector is given 2.39 into 10 power 6. Instead of r, I can take it as rho, right? Cos phi into a rho, ampere meter. And it exists in free space they are giving. Then find the magnetic flux phi crossing the surface defined by phi equal to 0 to pi by 4 and z equal to 0 to 1 meter. Yes, we will draw this surface. Then it is asked to find out the magnetic flux phi. Phi is equal to surface integral of b dot ds. If you don't remember, just remember the definition of magnetic flux. The flux passing through units are phi by s, right? So that you can recall this. But h is given. So we know that the relationship between b and h. B is equal to mu naught into h. So mu naught can be taken out. Surface integral of mu naught is taken out. H into ds. Is it fine? So mu naught is constant. It's taken b equal to mu naught h. Okay, call this as equation 1. H is given. Then what about ds? Okay, let me draw the diagram first. X, Y, Z. Yes, z is given, phi is given, and rho radius. Okay, phi is 0 to pi by 4. Phi is 0 here in the xz plane, and as we move it is pi by 4, right? Okay, let me try to draw it here. Okay, let me take the dotted line for this. I'll tell you why I'm taking dotted line. Okay, if I measure the phi, it is 0 to 90 degree, but here they have given 0 to pi by 4. Pi by 4 means somewhere in between it will come. So let me draw this surface correctly now. Right, this is the correct surface. I hope you got it. Right. So phi is equal to 0 to pi by 4 here, from here to here. Right. Here phi is 0 here, and here it is pi by 4. Right. So 0 to pi by 4. Then z is 0, z equal to 0. This bottom z is where z is 0 here, z equal to 0, and top surface z is equal to 1, right? So radius is rho. Okay, then h is given, and it is in the radial direction. Everywhere the field is, magnetic field lines are living in radial direction. What about the differential surface here? It should be in radial direction, right? So that surface should come here. This is the small differential surface area along radial direction. So AR, it is living in this radial direction, AR or arrow. Is it fine? The next, the same thing, the scale factors 1 rho 1, the differential elements are d rho, d phi, dz. So I want the differential surface area along rho direction, leave this and multiply other two, 1 into rho d phi dz. So rho d phi dz into arrow. Yes, once this is found out, take the dot product of h dot ds, right? So phi is equal to mu naught is how much? 4 pi. This one, equation 1, mu naught is 4 pi into 10 power minus 7 into surface integral of, what is h? Let me write it, 2.39 into 10 power 6 divided by rho into cos phi. I will not write arrow because arrow dot arrow will be 1. So next ds is rho into d phi dz. Rho will get cancelled. So next phi is varying from 0 to pi by 4. Z is varying from 0 to 1. Right? Okay, integrate this. So 4 pi into 10 power minus 7 into 2.39 into 10 power 6 can be taken out. Right? So next, what I'm left with, just let us integrate. Right? Okay, first we'll integrate with respect to, only cos phi is left out, right? D phi dz. Let us integrate with respect to z. Any of z is constant, so it is varying from 0 to 1. The next differentiation, integration of cos phi is sin phi, and phi limits 0 to pi by 4. So we'll calculate this. So 4 into pi into 10 to the power of minus 7 into 2.39 into 10 to the power of 6. So I'm getting it as 3.003. 3.003 into open bracket, this is over. Next, upper limit minus lower limit, I am getting 1 into sine of pi by 4 minus sine 0 is 0. So sine of 180 divided by 4, sine of 180 degree divided by 4. So I am getting it as 0.707. 707.1. So multiply with 3.03 into 3.003. So I am getting this as phi is equal to 2.1234 Webers. Right, you can check the answer here, right? 2.1236 Webers. Okay. Choosing this differential surface area is important because h will be given in which direction, right? Blindly you can say that it will be in this direction only. If you take in other direction, AR, it will be differential surface along radial direction only. If you take along phi and z, it will cancel out. A phi dot arrow is 0, az dot arrow is 0, right? Okay, next problem, I will leave it to you people, you solve it. This is the solution of that same problem, whatever I have solved here. Okay, you will solve this problem. I will give some time. In cylindrical coordinates, B vector is given 2 by R into A phi Tesla. B vector is given 2 by R means rho here into A phi. 2 by rho into A phi Tesla. Then determine the magnetic flux phi. It is defined by rho lying between the, instead of I told no, it is rho 0.5 to 2.5 and Z lies between 0 to 2. Okay, I'll stop recording, but you do it and tell me the answer.